Hello everyone, my name is Chris Perfetti, and this video will cover uncertainty quantification in nuclear engineering applications. This video is intended to be part of a lecture series organized by the American Nuclear Society, or ANS. The idea is that different ANS professional divisions will produce introductory videos on different subjects to educate our members on what our society does, and also to foster collaboration between folks within the society. I'm on the executive committees for the Mathematics and Computation Division and the Reactor Physics Division, and I'm involved with the Criticality Safety Division of the American Nuclear Society too. The topic for this lecture, which is uncertainty quantification, is relevant to each one of these three divisions and is also broadly applicable to quite a few other ANS divisions as well. Whenever we perform some kind of simulation or experiment, it's unavoidable that there will be some degree of uncertainty present in our system. In nuclear engineering, these uncertainties tend to be uncertainties in the density of materials, uncertainties in the number densities or enrichment of fuels, uncertainties in the temperature of different parts of our system, or very often, uncertainties in our nuclear cross-section data. Our goal in discussing uncertainty quantification is to better understand how uncertainty impacts our simulations and experiment, and also to better understand the sources of uncertainty so that we can mitigate their impact. Historically, a lot of uncertainty quantification has focused on criticality safety applications, where we want to understand how uncertainty in cross-section data affects margins of subcriticality. There is very promising potential for some of these uncertainty analysis methods to be applied to all different sorts of nuclear engineering fields. When we discuss uncertainty quantification, which is sometimes known as UQ, there are two main types of uncertainty that we consider: aleatoric uncertainty and epistemic uncertainty. Aleatoric uncertainty can be thought of as random error or statistical noise. It refers to small variations in a measurement that occur when that measurement is repeated, no matter what. For example, if you're playing darts, no two dart throws will ever land in the exact same spot, regardless of how skilled the player is. Even if you're the darts world champion, or if you build some hyper-intelligent dart-throwing robot, each dart will land in a slightly different spot. This difference might only be a millimeter or less, or if I'm the one playing darts, a couple of meters or less, but there will always be some unresolvable difference. In contrast, epistemic uncertainty describes uncertainty from variables that we could in principle know, but that we don't know in practice. For example, we don't exactly know the uranium-235 fission cross-sections, but we could in theory improve our U-235 cross-section evaluations and reduce the impact of this uncertainty on K-effective simulations, for example. If we understand the impact of these variables and their uncertainty on our simulations or experiments, then we can in theory calibrate these parameters in a way that reduces the uncertainty that they introduce. Because this epistemic uncertainty stems from parameters and data that we can control and improve, uncertainty analysis methods generally focus on epistemic sources of uncertainty. We can understand the impact of uncertainty in these parameters, examine whether different systems share the same sources of uncertainty, and even use the observed results of experimental measurements to try and calibrate our uncertain parameters, thus improving our ability to accurately model different phenomena. Before we move on, I've mentioned how we can't really treat sources of aleatoric uncertainty, but there is one thing we can do with them: uncertainty propagation. We can use uncertainty propagation to understand the impact of this statistical noise in our simulations. For example, we can use uncertainty quantification to propagate the impact of stochastic noise in Monte Carlo simulations, which is very important when comparing the results of Monte Carlo simulations to experimental benchmark measurements, since both the Monte Carlo simulation and the benchmark measurement contain some uncertainty. Moving on, what can we do to understand the impact of different sources of uncertainty? Well, in general, there are two main types of uncertainty quantification: forward uncertainty quantification and inverse uncertainty quantification. Forward uncertainty quantification is the easier of the two to understand. Forward uncertainty quantification aims to understand the impact of uncertainty in input parameters on our output parameters. We'll discuss this in more detail, but some examples of forward uncertainty quantification include propagating cross-section uncertainty to eigenvalue estimates in criticality safety simulations, or figuring out how much uncertainty is contained in a reactor's axial power peaking factor, or estimating the amount of uncertainty in the amount of plutonium-239 that's present in spent nuclear fuel. In contrast, inverse uncertainty quantification methods take a series of observed results and use them to calibrate certain input parameters or model parameters. Examples of inverse methods include using criticality safety benchmark measurements to calibrate data for cross-sections that are difficult to measure directly, or fitting evaluated nuclear data parameters in NDEF to differential cross-section measurements, which is what the SAMI code does, or using detector signals from portal monitors to infer if some unknown package contains fissile material. Forward uncertainty quantification methods can generally be divided into two classes of methods: stochastic methods and deterministic methods. Unfortunately, these methods share the same name as two kinds of radiation transport methods, stochastic methods and deterministic methods, which makes our endeavors unnecessarily confusing. But please bear in mind that stochastic uncertainty quantification methods and stochastic radiation transport methods are two completely different things, as are deterministic uncertainty quantification methods and deterministic radiation transport methods. You can perform deterministic UQ analyses using a stochastic radiation transport code, such as MCMP, and likewise you can perform stochastic uncertainty quantification analyses using a deterministic transport code, such as CASMO. The two fields are completely decoupled, even though they unfortunately share the same terminology. Stochastic uncertainty quantification methods rely on repeatedly and randomly sampling uncertain input parameters and observing the impact that this sampling has on output variables. As we examine the distribution of output variables, we can determine the standard deviation of our simulation results, or even the covariance between different parameters. Stochastic UQ methods are nice because of how extremely flexible they are. As long as you know how uncertain your input parameters are, you can generate a distribution of perturbed output variables and measure their standard deviation. As we'll discuss later, this is in contrast to deterministic UQ methods, where we can only generate uncertainty estimates and sensitivity coefficients for parameters that we can estimate using an adjoint function. Don't worry, we'll talk more about adjoints later. The downside to stochastic UQ methods is that they don't provide as much insight as deterministic UQ methods. Yes, they can give you estimates of the standard deviation of output parameters, but as you'll see later, deterministic methods can give sensitivity coefficients that describe the impact of input uncertainty to a much higher degree of resolution, which enables all sorts of interesting mathemagic. Another significant downside to stochastic methods is their speed. Stochastic methods are often very slow because you have to perform so many repeated simulations with perturbed input parameters. This issue has been mitigated in part thanks to modern computing resources and large computational clusters. And to be fair, computer runtime is much cheaper than human time, and computers will happily continue running all through the night and all through holidays. But still, stochastic UQ methods will still often have issues with runtime and simulation efficiency. Some common questions arise when using stochastic UQ methods, the first of which is usually, how long do I need to run the simulation, or in other words, how many times do I need to randomly sample my uncertain input parameters to get reliable results? In general, you need to run about 300 random simulations for criticality simulations that are perturbing cross-section data, but for other problems there is a reliable way of knowing how many simulations we need to run. This way is to use Wilks's theorem, which says that the log likelihood for the true value of some variable theta is about equal to the log likelihood of the estimated value of that variable, theta hat, minus the chi-statistic for that variable and to whatever degree of confidence is desired. Without delving too much into the statistics, the long story short is that we can use Wilks's theorem to generate confidence intervals for a group of random samples. If that confidence interval is larger than we would like it to be, then that means that we have to run more samples. Another common question with stochastic UQ methods is, can we minimize the number of samples that are required? This is an understandable question. Stochastic sampling is often quite slow because of the sheer number of samples we have to take, and anything that we can do to reduce this runtime is often very helpful. The most common approach for accelerating convergence of stochastic methods is to employ a sampling methodology that draws our samples as efficiently as possible. While the default approach is to draw our samples completely randomly, one method that is generally more far efficient is known as the Latin hypercube sampling, or LHS method. Latin hypercube sampling was first theorized by Michael Mackay at Los Alamos in 1979, and was also independently theorized by the Latvian engineer, inventor, and professor Wave Iglesias. Latin hypercube sampling works by dividing your variables into a number of equal probability intervals, similar to what we do for stratified sampling. In this case, the number of intervals we have is equal to the number of samples we want to draw. We then sample the variables so that each variable can only be sampled from each stratified range just once. An example shows this 2D chart with 2 variables that we want to sample and 4 intervals, meaning that we want to draw 4 samples. Once a variable is sampled from an interval, indicated by the green circle, the other samples cannot sample again from that interval, indicated by the blocking yellow lines. I like to think of Latin cube sampling like a game of Sudoku. Sampling a variable from an interval excludes that interval from all that variable's future samplings. This example shows Latin hypercube sampling for a 2D, 2-variable case, but in theory you can apply Latin hypercube sampling to as many variables as desired, kind of like how you could play 3D Sudoku if you are a madman. Latin hypercube sampling is an effective sampling method because it forces samples to be distributed through your phase space fairly evenly. You won't ever have a random variable that is sampled from the same place twice. This of course introduces a bias in the sampling methodology because having samples drawn with the same value multiple times is something that should happen at least sometimes. But in general, Latin hypercube sampling is preferred because it guarantees that you'll never have any blind spots in the phase space that you're sampling. We'll finish our discussion of stochastic EQ methods by briefly discussing sensitivity coefficients, which is something that we'll discuss in significantly more detail later. The sensitivity coefficient, S for R in sigma x, describes how changes to, or uncertainties in sigma x, will change the value of R. Essentially, sensitivity coefficients are a fancy name for relative derivatives. Sobel indices are a cousin of sensitivity coefficients that allow for understanding the sensitivity of multiple variables in combination, but they're not something that we're really going to discuss here. Sometimes when we're using stochastic UQ methods, we will want to develop sensitivity coefficients. Examples of this include when we might be trying to optimize a capture to fission ratio in some reactor design. In the area of criticality safety, these sensitivities have been used to understand the impact of cross-section uncertainties on a system's eigenvalue, but they can also be used for things like design optimization or for accelerating simulations a la Newton's method. When performing stochastic UQ analyses, we can examine the range of outputs for a variable R as a function of some input variable sigma x. From here, we can more or less use the secant method to estimate the sensitivity coefficient for R as a function of S by examining our range of outputs. This approach for estimating sensitivity coefficients has some significant advantages and some significant disadvantages. The biggest advantage to this approach is its flexibility. We can obtain sensitivities for any system and any output response that we can simulate using stochastic UQ methods. You just need to examine the range of output variables as a function of the input perturbations. As we'll see later, deterministic UQ methods can only compute sensitivity coefficients for terms where we can derive adjoint functions, and deriving adjoint functions can be an extraordinarily difficult endeavor, and sometimes even more difficult to implement into a code. The biggest disadvantage for stochastic EQ methods when computing sensitivity coefficients is the curse of dimensionality. Let's assume that we want to compute sensitivities for some uncertain cross-sections in a criticality safety simulation. We'll assume that we need to sample each variable 5 times to obtain an accurate estimate for its sensitivity, and first that we want to compute first-order sensitivity coefficients, which means that we sample our variables one at a time. Let's assume that our cross-section uncertainty data is grouped into a 252 group format, which is one of the go-to formats for the scale code, and that we have 5 isotopes in our system, and that each isotope has 4 reactions that we want to sample. This means that we have 5,040 independent parameters to sample and that we must perform 25,200 simulations to obtain all of our sensitivity coefficients. That sounds like a lot of simulations, and from here, things will only get worse. This math assumes that each sensitivity coefficient will be sufficiently resolved after only 5 samplings and will have no stochastic convergence issues. In reality, this assumption is never true. Even worse, we may want to obtain higher order sensitivities than just simple first order perturbations, which require that we sample every uncertain parameter simultaneously. If we take this simultaneous sampling approach, then our required number of runs equals our number of parameters to the power of the number of runs per parameter, which in our sample problem is equal to 3.252 times 10 to the 18th simulations. And this is just for a relatively simple criticality model. This doesn't even approach how many samples we would need for a complicated system. So how do we overcome these hurdles? And how do people use stochastic UQ methods to estimate sensitivity coefficients? The answer is that they generally don't unless they're analyzing a system with a very small number of uncertain variables. Other workarounds include approximating our sensitivity coefficients using Sobel indices with an insufficient number of samples. In this case, Latin hypercube sampling can help our undersampled problem to reach convergence. Alternatively, we could feed some random samples to a machine learning algorithm to generate a surrogate model for our system. Once we have the surrogate model, we can use it to estimate sensitivity coefficients for our system's uncertain variables with much greater ease, or we can just use a surrogate model to predict the behavior of our system under perturbed conditions. However, sensitivity-based uncertainty quantification is typically performed using deterministic uncertainty quantification methods, which we will now discuss. Deterministic sensitivity and uncertainty quantification methods rely on computing sensitivity coefficients to power their analyses. Once we have these sensitivity coefficients, then we can propagate uncertainty in nuclear data or model parameters, or also optimize a system's design, or perform several other very insightful analyses, which we will discuss later. Deterministic sensitivity coefficients are not computed by perturbing any data, as in stochastic UQ methods, but are computed using mathematical expressions. One example of these expressions is the first-order perturbation equation, which we have shown right here. This equation allows us to understand the sensitivity of critical eigenvalues to neutron cross-section data, and it relies on having some expression for phi star, which is the adjoint flux right here. We'll talk about adjoints more in a minute, but in general, the downside in deterministic UQ methods lies in the fact that we need to obtain mathematical representations for sensitivity coefficients, which are often difficult to obtain and often even more difficult to implement in codes. As a result, deterministic UQ methods are less flexible than stochastic UQ methods because they are limited to analyzing systems for which we have mathematical representations of an adjoint flux. In contrast, stochastic methods can be applied to any response that we can simulate using perturbed input parameters. However, we'll see that deterministic sensitivity coefficients generally have orders of magnitude less noise than stochastic sensitivities. Furthermore, they do not suffer from the curse of dimensionality, and we can often compute sensitivity coefficients for every single piece of nuclear data in a system by using just 1 or 2 simulations. Because deterministic sensitivities contain such a higher degree of resolution than stochastic sensitivities, they generally provide an unparalleled degree of insight for sensitivity and uncertainty analyses. So what is this adjoint flux that we need to compute sensitivity coefficients? The adjoint flux, which is sometimes known as the importance, describes how much a certain particle will contribute to some response in the system. If, for example, our response is the eigenvalue of a critical system and our particle is a neutron that thermalizes and enters plutonium fuel is very important since it's very likely to induce a fission and contribute to the eigenvalue of the system. Conversely, a neutron that is captured before it reaches the fuel is not important, just as a neutron that leaks from the system by hitting vacuum boundaries is also not important. So how do we compute these adjoint fluxes? Getting adjoint fluxes for new responses as a function of new data inputs is the main hurdle for deterministic UQ methods. In general, computing these adjoints requires intense mathematics and complicated algorithms, which in my humble and unbiased opinion are perhaps the most complicated algorithms in radiation transport. Currently, our theory allows us to compute adjoints in continuous energy Monte Carlo codes for eigenvalue responses, reaction rate ratios, and some other bilinear ratios. These sensitivities can be computed as a function of cross-section data, probability distributions, resonance parameters, and some dimensional information. There is ongoing research to expand these adjoint functions both to more responses and to more input data. So what can we do with these sensitivities once we have them? I already mentioned how we can use sensitivities to optimize reactor designs, such as by trying to increase the capture-to-fission ratio in an isotope production reactor, or by trying to minimize the dose rate outside of a shield. But another thing we can use sensitivity coefficients for is uncertainty propagation. Assuming that we have some response R that is uncertain due to inaccuracy in nuclear data, we can determine the variance in standard deviation in R by combining our sensitivity coefficients with the cross-section covariance data according to this equation, which is commonly known as the sandwich equation. While stochastic UQ methods can directly assess the uncertainty in responses just by examining the distribution of perturbed output values, deterministic methods must use the sandwich equation. One important thing to note here is that we cannot simply multiply one vector of sensitivity coefficients by a vector of nuclear data uncertainties. This is because our nuclear data uncertainties contain various correlations. For example, when a neutron scatters, it's difficult to tell if that neutron scattered due to an elastic reaction or an inelastic reaction. So there is thus some correlated uncertainty between elastic and inelastic scattering reactions. Similarly, a data measurement might use a known sample of, say, uranium-235 to calibrate a detector that is being used to measure americium cross-sections, which introduces a correlated uncertainty between the uranium-235 and americium cross-section measurements. This matrix of correlated nuclear data uncertainty is known as the covariance matrix for nuclear data. Understanding the uncertainty that lies in nuclear data is a little like seeing how the sausage is made. Measuring and evaluating nuclear data is an extremely difficult process that requires fitting nuclear models to highly uncertain data. Because data evaluators must contend with so much noise in data measurements, there is a fair degree of uncertainty in nuclear data. For example, here's a plot of a 1D representation of the uncertainty in the uranium-235 fission cross-sections. One might think that we know the uranium-235 fission cross-sections exactly, but that is not true at all. These cross-sections contain as much as 4% uncertainty at certain ranges, and even worse, here's a plot of the uncertainty in uranium-238 capture cross-sections, which contain about 21% uncertainty at certain energies. Both of these isotopes and reactions are very common in nuclear reactors, and one might think that we should know them better than this. This somewhat frightening look behind the curtain of nuclear data emphasizes why uncertainty quantification is important. Significant uncertainty exists in our nuclear data, and to design reactors with any degree of confidence, we must understand how this nuclear data uncertainty propagates through our simulations. Deterministic sensitivity methods have one other fascinating use that we will discuss: similarity assessment. Let's say that we're trying to license a new reactor design, and that this design is so clever and so paradigm-breaking that there are no other reactors like it. To license our reactor, we'll need to prove to the NRC that our simulations can predict how our system will behave. But how can we do this without building a whole series of costly, time-consuming experiments? One approach is to see if there are any existing benchmark experiment measurements that are similar to our new design. If our code is accurate for these similar systems, then it should be accurate for our new application. So how do we assess similarity between these two systems? Well, if we're using a very high-fidelity modeling and simulation code, such as MCMP or Kino or Serpent, with a very detailed and presumably accurate model of our system, then any inaccuracy in our simulation should be caused by uncertainty or errors in our nuclear data. So to assess similarity between our benchmarks and our new application, we should examine which benchmarks share the same sources of nuclear data-induced uncertainty as our application. We can use this modified version of the sandwich equation to do just that. By combining our sensitivity coefficients for one system's response, R1, with another system's response, R2, and weighting these sensitivities by the nuclear data covariance data, we can compute sigma R1, R2, which is the amount of nuclear data-induced uncertainty that is shared between the two systems. By dividing this shared uncertainty by sigma R1 and sigma R2, we can develop something like a Pearson's correlation coefficient, C sub k, that describes the fraction of nuclear data uncertainty that is shared between the two systems. C sub k ranges from 1 to -1, where a value of 1 means that the two systems exactly share all of the same identical sources of uncertainty, and where -1 means that all uncertainties are completely anti-correlated. In practice, a code validation study would compute sensitivity coefficients for a target design and also for a large number of benchmark experiments. After we have these sensitivities, we'll find which experiments share the highest C sub k values with our target design, and then use the known computational bias for these systems to extrapolate a computational bias for our design. In criticality safety applications, codes like USL stats use linear regression to develop confidence intervals on the upper subcritical limit for criticality safety systems. And codes like Whisper use these similarity coefficients to do a weighted non-parametric analysis to obtain margins of subcriticality, where these C sub k coefficients are used in weighting the observed computational biases from different benchmark experiments. In my, once again, humble and completely unbiased opinion, there is an enormous potential to use these similarity coefficients to assist in validating simulations for next-generation reactors and microreactors, but little activity exists in this area just yet. This concludes our summary of forward UQ methods, which again aim to understand the impact of uncertainty in input parameters on output parameters. Before we conclude this lecture, it's worth spending some time discussing inverse UQ methods, which use series of experimental and computational results to calibrate uncertain input parameters or input models. In essence, we identify some discrepancy between a high-fidelity simulation result and an observed experimental result, and we adjust the input parameters and/or data in our computational model until its results match the observed measurement. This data calibration process generally uses Bayesian statistical methods, such as the generalized linear least squares method, which has been implemented in several codes. The SAMI code calibrates nuclear model parameters in hopes of generating evaluated nuclear data, which is the stuff in those big long NDEF ASCII files, that match differential cross-section measurements. Another data calibration code is SURFER, which uses the results of critical experiments to roughly calibrate multigroup cross-sections, which can then be used to extrapolate a computational bias for criticality safety simulations. It's worth noting that the SURFER data calibration and data assimilation code uses deterministic, i.e. adjoint weighted, sensitivity coefficients to determine the impact that a data perturbation will have on the simulation's results. Without these high-resolution sensitivity coefficients, we would have to re-simulate each and every case to determine the impact of each little data perturbation, which would result in an infeasible, curse of dimensionality-esque enormous number of simulations. One thing worth noting with Bayesian calibration methods is that they generally assume that all bias is due to epistemic uncertainty, which again is uncertainty in things that we could know, and that none of our bias is due to random, unavoidable aleatoric uncertainty. Thus, Bayesian calibrations that use a small number of experimental data points will always run the risk that their calibrations will be incorrect because they force data to be calibrated to account for aleatoric uncertainty. This risk can be avoided by using enough experimental data points in a calibration to ensure that the random aleatoric uncertainty cancels out, but this is sometimes difficult in nuclear data calibration studies due to the enormous number of nuclear data parameters that are being calibrated, which does frequently make these calibrations quite under-constrained. Some other inverse UQ analyses include using inverse transport methods to infer the identity of an unknown radiation source, which is helpful for trying to determine if someone is trying to smuggle weapons-grade uranium through a portal monitor. Another application of inverse-like uncertainty quantification methods includes using machine learning algorithms or neural networks. In this case, we can feed some simulation results or computational bias information to the machine learning algorithm and then use these algorithms to predict the response or bias in some other system. This concludes our very brief foray into uncertainty analysis methods. This lecture is of course tainted by my bias towards certain uncertainty quantification methods. My research deals with deterministic UQ methods, which I thus prefer over stochastic UQ methods, but my goal here has been to give you all a brief glimpse into the world of uncertainty quantification. Uncertainty quantification is a rapidly growing area, and I think there's a ton of potential to apply established UQ methods, such as those from criticality safety, to other nuclear engineering fields. And I hope that this lecture will stimulate some discussion and cross-collaboration on uncertainty quantification methods.